Doctor, no, you are still recording.
Okay. Good morning. Today is November 18th, Thursday. We're going to basically complete an example about this calculation of the equivalent forces. When you have distributed forces on a beam, you may calculate the equivalent forces and moments. Okay, that's the objective of this session. At the beginning, I will review the derivation of the stiffness matrix. That's something that we didn't do last session, using this approach, this potential energy approach. Okay, so we're going to do these two things. And at the end, I will have some time to answer questions about the project. Okay, that's the agenda for today. Genesis, can you see my PowerPoint?
Yes, doctor.
Okay, so this is what we did on Monday. Let me go back here. This is the potential energy. We have the potential energy is equal to the force. In this case, it's dF because it's considering just one single element, differential element, multiplied by the displacement that this element can take. Okay, this displacement, we're going to take it from the assumption that we can interpolate from the joint values. It's just an assumption, okay? Because in this case, this n vector, it's a polynomial that we assume. Okay, from there, we can replace it into here, okay? This is the vector of the displacements of the joints that doesn't depend on x or y or z. So we can take it outside the integration, okay? And the result is something like this. Okay, so this is the distribution of force per unit length on the element. See, you multiply by the vector of the polynomials for interpolation, and you integrate it in the whole element. Okay, so in this case, we're going to have 4 elements. Okay, this vector has 4 elements. The first one gives you the equivalent force on the left, on the first joint of this element. The second will give you the equivalent moment. And similarly, for the third and fourth, will give you the force and moment equivalent on the right, on the second joint. So this procedure is a very consistent way to calculate equivalent forces and moments from any distribution of forces. Okay. Remember, we are discretizing. That means that we only care about what happens in the joints. We do not, it's simplification. We do not, we neglect what happens in between the joints. So in this way, we can take any distribution, this thing here, and calculate the equivalent forces which must be applied on the joints. So you can follow this procedure with any distribution that you have. But the problem is that this is not exact. So we have to be careful when we do this. We always have to think about how good is this approximation. And the best way to do it is to check the convergence, as we were discussing at the beginning of the session. Always, 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 always. Okay, and then we took the simplest case, which is the uniform load. In this case, we consider the something similar to the weight of the element, distributed weight. You see that this is little w. That means this is weight per unit length. we multiply by this vector. This is the n vector, and we integrate. This is what we obtain. So we take half of that and put it on the left, the rest on the right, and then, oh, we are missing a negative here, I guess, right? People, can you check your class notes? I think, yeah. For some reason, in some cases, I miss some of these signs. Anyway, you have a negative. Oh, see, you see it erases. So this is negative.
Doctor,
okay.
I have question.
Yeah.
This is for a load distribution and constant, no?
Yeah.
Yeah, it's very different. Have the load distribution line.
Yeah, but what you can do is you can integrate.
Yes.
You can set up this W in a different way, and you just let me erase, and you just integrate. That's all. In general, some of these integrations in a computer program, they are done in a numerical way. But in general, since we are considering simplest cases, we can take this and integrate analytically. Okay, Jesus Christ. Okay, so this is minus L squared divided by 12. He doesn't want to this spot. Okay, so that's it. Okay, so this is what we have done. We had this, and now we have this. Okay, X to the right, Y upwards. So this is the positive external direction. So in this case, since we're pushing upward on the right joint, you see that it tends to rotate in that direction, which is opposite to the positive. That's why we need this negative here. We have to be careful with that. In the case of surface forces, it's very similar, very, very similar. But instead of having a body forces, we have contact forces. We need the contact to the surface of the element, but the rest is the same. So this is force per unit length. This is little p, and this is due to the pressure. Let's say the pressure on the surface of the element. And then we can proceed to multiply with this vector and then integrate in exactly the same way as we did before. We missed a dx here. Let me check. Let me correct this. Here we need a dx. Okay. This is dx. Okay. And then this function could be anything. And then you multiply it by this and then get the result. And the result is going to be forces and moments on the ends. This is what we're saying here. Okay, and then we said a little bit about what happens when we have a hydrostatic pressure. Okay, in this case, we have a variation of the force. So this is not constant. Okay, so we have to calculate the pressure here, the pressure there. We multiply that by the spacing between frames, and this data is given to you, was provided to you by Engineer Isaac. So we have this product. This is a specific weight, height, from the free surface to the point where you want to calculate, and this is the spacing between frames. So the result of this is force per unit length. So we know this. In this point, we can calculate the same parameter in this other point, and then we can do the linear interpolation. And once we know this, we can integrate and calculate the equivalent forces. But remember that we have to do the equilibrium in the global stiffness, in global reference system. So what we have to do is we can calculate, knowing these values, we may calculate the equivalent external forces in the joints. This is something that somebody asked this morning. When we have this case, we have this frame, and this frame is welded to the plate. So in order to have the inertia, we have to consider both. We have to consider the plate and the stiffener. For example, if we had an angle here, in that case, we should include all of this in order to calculate the inertia. We have to calculate where the neutral axis is, and then calculate inertia with respect to that axis. Similarly for this case. So in general, for example, if you have a bottom with different thickness than on the side, you will have two values for the inertia. And that's something that we can handle easily with finite elements, because we can take a bending stiffness for every element, and we can set it different. So there's no big problem for that. Okay, people, let's continue. Today is November 18th. So we have, we are trying to apply the method of minimum potential energy. This potential energy of the external forces we have already calculated. We need to say a little bit about U, okay? So, this is from last semester, okay, from the class of structure, from last semester. We know that U is equal to 1/2, and then we integrate in the whole volume the product of epsilon x times sigma x for the case of the beam. Okay, because in this case we have only one single element of the stress tensor. Okay. Also, okay, this is force per unit area. This is length cubed, so the product will give you U. Also, using Hooke's law, see, if we use Hooke's law, immediately we think that a material which is stressed below the yield point or the elastic limit. So in this case, since we have one single element, we can say that sigma x is equal to Young modulus times epsilon x. So from this, we're going to go in a similar way as we did for the case of the bar and try to derive, not differentiate, derive the stiffness matrix of the beam element. Okay, so let's do it. From beam theory, we recall that epsilon x is equal to minus y v, comma, xx. Okay, and this is basically the kinematic hypothesis. Okay, now this we're going to take, for this, we're going to take the approximation, the finite element approximation. And then in this case, we're going to work in the local reference system. Okay, so this is an approximation because we're assuming that inside the element, the distribution of the displacement is cubic. And applying finite element interpolation, okay, this epsilon x, which is this one, we're gonna take this function and we're gonna say that it is equal to minus y, and this is going to be equal to, remember, these are the joint displacements. This is a vector, I transpose it, so this is a row, and we have to multiply by the second derivative, okay? Second derivative with respect to x of the polynomial that we employed for interpolation. Okay, so this is a row, this is a column, the product is in a scalar. Okay, this vector n is completely known, so this is known. This is something that we try to determine. And if we use the Hooke's law, we can calculate sigma x that we're going to replace here. But since this is a scalar, we can switch the order of these two elements. We can say that this is equal to minus y e, and we can take these two transpose. So this is the second derivative with respect to x of the transpose of that, and multiply by the vector of the displacement joints, of the joint displacements. So this is a vector, this is a row, don't forget this. So the product is a scalar. This is a row, this is a vector, and again, the result is a scalar. Now, let's replace these two expressions, okay? Well, where is my, here is my. Okay, so let's take this, let's take that, and replace it into here and there. So we have how to calculate the U, that's the strain energy, as function of the displacement vectors. So, replacing in U. So U is going to be the integrate, well, 1/2, we put it well to the left, and then we can integrate. We put dv here, and we put it like this. So dx, dA, you will see that in a minute. Why? Because we see that there is a dependence on x explicit, but there is no dependence on y, on y or z. That's why we put it like this. Okay, so first we include epsilon. So epsilon is equal to d transpose, so this is a row, times the second derivative of the n vector. And then we need a y, we put it here, there. We need a negative, but we also have another negative in the stress. So at the end, the two negatives will give you a positive. And then what? Then we have here, we have the stress. So it's going to be similar to that, but we need the Young modulus. So we're going to have an E, another Y, which will give you an square. And then these two elements, we're going to transpose them. So I'm going to take this, transpose. So it's going to be the second derivative with respect to X, but transpose. So this is a rho, and multiply by G vector. Okay, here, so this term here depends on X. This term here depends on X. This Y goes with this Y. So what we can do is we can separate a little bit according to the dependence. So let's say that N depends on X. So we can rearrange this expression. So we said U is equal to 1/2. And then we have this D transpose. And then first we integrate from 0 to L. So this is in this part here, I'm going to include all the terms which depend on X. So we have this term here because we have here N. So it's going to be the second derivative with respect to X of N. So that's the vector. These two do not depend on X. These depend on X. So that's the second derivative with respect to X squared times N, both transpose. So this is a rho. And then we have the integration in the area. And we have Y squared times E. And then we have this other term. There. Let's see. This is a vector. So it's going to be 4 times 1. This is a row. This is going to be 1 times 4. Okay, this is a vector, 4 times 1. And this is a row, 1 times 4. Okay, and as a result, you'll see that this part here will give you a matrix 4 by 4. This term here, anybody recognize this term? Mr. Nevares, can you recognize this term, this integration, what it will give you?
Inertia.
Exactly, that's the inertia of the section. So you have E, I sub C, and we assume that they are constant. So we can take those outside the integration. So we can say that this is U, is going to be equal to 1/2 E, I sub C. Then we have the rho, and then we have to integrate from 0 to L in X, and we have this vector. The second derivative times this is a rho. The second derivative is like the transpose. We have this already out here, so we have the E also up here, so we have to multiply only by this other vector. There. And this, or including the EI, let me put the EI in this spot. And I have to erase that. Sorry about this. And the rest is this. So as we said here, this is a 4x1 vector. This is a 1x4 row. So the result, all of this is going to be a matrix 4x4, and this is our very famous stiffness matrix. So this is the stiffness matrix deduced, as we can see, using minimal potential energy theorem. Okay. Any questions so far, people? We did this in chapter 2, in the previous chapter, using the direct method. We consider, remember, the equilibrium of forces and moments of the two joints directly. Well, we still don't have the final expression, but we're going to have it in a minute. But yeah, that it's going to be the same. It's going to be the same. But in this case, the approach was totally different. Okay, we said, okay, we're going to have a potential energy, and that's going to be the minimum. So let's complete it. Okay, so to do this, we have to remember these elements, and then we have to differentiate twice. So we can say from chapter 2, so the n vector is going to be 1 over L cubed. Then we have 2x cubed minus 3Lx squared plus L cubed. The second is x cubed L minus 2x squared L squared plus x L cubed minus 2 x cubed plus 3 x squared L. And finally, x cubed L minus x squared L squared. This is a vector. And you can see that if we evaluate this vector at 0, I get here, I get L cubed. Divided by L cubed, I give you 1. If I evaluate this at 0, 0, 0, 0. So you multiply this by the vector D, and you get the displacement on the left end, as we should be. You evaluate this at L, this is 0, this is 0, and this is 0. And this thing here is going to be L cubed divided by that will give you 1. So the product of this times D will give you D2Y, which is the displacement on the right end, on the right joint. Now, we need to differentiate this twice. So let's put it like this, okay, to save some time, comma, XX. So it's going to be 1 over L cubed okay, so, and what I'm trying to do here is just apply this multiplication. Okay, so we need to differentiate these twice. So the first element, we get what? We get 3, 2, that's 6, and 2 here, that's 12, right? So it's going to be pen here, so it's going to be 12x. And from here, I got a 2 minus 6L. There. The next one, I got 6 here. So it's going to be 6xl. And from here, I got minus 4l squared. The next one, this one here, I got 6 and 2 12, but negative 12x. I got 2, and that's 6l. And finally, I got 6xl and minus 2l squared. There. Now, let me go back. Yeah. So remember, this is a vector, this is a row. So each one of these elements, this is a 4 by 4 matrix, is going to be the result of taking one of these elements, okay, that give you the row, multiply by each one of these, that'll give you the column, and then we have to integrate from 0 to L. Okay, so let's, just to check, for example, let's check one element, only one element. Okay, for example, let's calculate the element K 2, 4. So it's going to be equal to what? So we take the second, from the second row, so we have this, I'm sorry, from this, the second row. So it's going to be 1 over L cubed. So it's going to be 6xl minus 4l squared. And multiply by the fourth element, so which is this one. So this is 1 over L cubed. And this is the fourth, is this one, 6xl minus 2l squared. What else? But we have to not only multiply it, but also we have to multiply by e sub I sub c and then integrate it in x. So let's put the e I sub c in the other side. And we have to integrate like that. See, all of these x's are local x's, okay? So it's going to be what? The integration of this times that, so it's going to be 36 x squared L squared. This times that, I'm sorry. What I'm missing the L to the 6. See, I'm missing this part here. So it's going to be equal to 1 over L to the 6. There. So it's going to be that, this times that, this times that will give you minus 12. And this times that give you minus 4. So it's going to be minus 16, I think, right? X, this times that, xl cubed. So this times that give you minus 12. This times that give you, oh, no, that's, I'm sorry. This times that give you minus 12. And this times that give you minus 24. So that's minus 36. So this is 3. And finally, this time that will give you plus 8L to the 4 dx. So that's going to be, I'm sorry, this is L to the cubed, L cubed. So it's L to the 6. So this integration in cubed, so it's going to be 36 divided by 3, that's 12. This is minus 36 divided by 2, so that's minus 18. And this is 8. And this, all of this is multiplied by, that's 4, that's 5th. There. So the result of all of this is what? 20 minus 18, that's 2. That's 2 over L. So K24 is equal to EI sub C divided by L times 2, I think. Right? Because units, always units. E, that's F L squared, I sub C, and then we have L. That's we got 3, so we got F times L. So remember, this 24, K24 is multiplied by phi2, and the result will have to give you moment. So in the matrix, okay, we have 4 rows and 4 columns. So this element is here. So this is K24. And it's multiplied by, this is phi 2z. And the result have to give you M2z. I'm sorry, M1z. So you multiply this is radians times that, which has units of force length, and the result is moment. At least the units are correct. Miss Pinkai, are you with me? Miss Pinkai, are you with me? Miss Pinkai?
Yes.
Okay, is there any question? No, everything is fine? So in this way, see, you multiply this vector times the transpose, which is a row, and you can take each one of these elements from the row, from the vector and from the row, multiply them, integrate, and that's the element in the correct place in the K matrix. So that's the process. Okay. So this is just another way to do the same thing, to get to the same point. And the point is that we obtain the stiffness matrix of the beam element. Okay, is there any questions about these people? Is there any question before we go to the break? No? Okay. Let's take a break. And when we return, we're going to do an example. And this example I posted as a PDF in the announcement section of the seed web. So please download it and have it at hand so you can follow my explanation. So we can take a break, 5-minute break now. So I need to stop this.